Welcome to IMS2020 Micro Apps. My name is Rafi Hershtig and I'm CTO of Kernel Microwave. Today's presentation is about reflective and non-reflective thin film LCR filters printed on Alumina. With increased data rate, we see that digital signals starts to behave as analog signals. Mismatches, reflective backwards energy are all impacting the RSSI, the bit error rate, or as the analog guys are simply call it, noise. For that matter, we are developing thin and thick film technology for planar filters and divide them into two groups. The reflective filters on the left are the filters that we are familiar with in the past 30-40 years. Low pass, band passes, high passes, band rejects, equalizers, multiplexers are all filters with S11, S22 over the pass band and total reflection over the rejection band. Non-reflective filters are also divided into two groups, the frequency domain and the time domain filters. Frequency domain filters exhibit good input and output match. S11 and S22 is matched up to 4 times FO. The time domain filters are the ones that are presenting a precise impulse response rise time with no oscillations. These are Gaussian-alike filters with good delay up to 4 times the FO. Here are some examples of reflective-alike filters that are the building blocks of more and larger block diagrams. High-pass filters with all-pole response that exhibit actually transmission zeros with a very broad passband. The transmission zero that we see in the S21 is due to a precise leakage amount of energy that we allow between the shunt inductors. These are all ER99 filters, starting with cutoffs from 6 GHz and all the way to 14 GHz in steps of 500 MHz. They are built on 25 mils alumina, an open frame package, and suitable for wire bonding, and they are being attached with solder epoxy, an operating temperature between -55 to +125 C. The next example is for two bandpass filters interdigital type with 5 resonators that cross each other at exactly 3 dB. S11 from the common port is broadband match. This is a unique solution for wideband multiplexers. The realization is made on thin film alumina 25 mils with temperature compensation. We're moving now to frequency domain non-reflective low-pass filters. Starting, for example, with N=5 low-pass filter, on the left, we are disconnecting the two ground nodes, and we are replacing this topology with N=9 on the right, where resistors are connecting the capacitors to the ground. The realization is in suspended substrate alumina, titanate structure. The inductors are the narrow lines. The capacitors are realized as broadside coupled lines, so the energy goes through the PC board. And the resistors are thin film technology. It's called suspended substrate because the substrate is suspended between two layers of air. Here is an example of a non-reflective frequency domain low-pass filter with one transmission zero, realized by the series parallel LC configuration in the center of the filter and exhibited in the S21 curve as an enhanced rejection in a prescribed frequency. This prescribed frequency can be, for instance, a second harmonic of a fundamental between the stages of an amplifier. The return loss S11 and S22 is matched up to 4 times FC. Switching to non-reflective time domain low-pass filter We understand that the motivation is that higher data rates impact BERT. Digital signals exhibit analog symptoms, such as impedance match, reflections, etc. Examining the step response of a Gaussian and a Chebyshev filter, we observe that the Chebyshev filter has a lot of ringing in red in the slide in front of you. And the Gaussian is a perfectly square wave, the blue response. However, the Gaussian has a very poor return loss. It is matched only at DC. The solution is a non-reflective quasi-Gaussian low-pass filter that we call TTC, transition time converter, matched S11 and S22 up to 4 times FC, and a very flat group delay up to 4 times FC. Transition time converters, or TTC, can slow down the high-speed oscilloscopes. They are perfect for BERT protocols that are calling for a precise rise time. They are reducing the overshoot and ringing, reducing the bandwidth, and less impedance match problems since the filters are absorptive. Below, there is a comparison of eye diagram of a 33 picosecond rise time from 10% to 90%, simulation, and 33 picosecond prototype hardware data. As you can see, there is a perfect agreement between the hardware and the simulation. So, what is the process of ordering TTC filters? Well, you start by going to www.klmicrowave.com. Then you get this page where you hit Products, Transition Time Converters TTC, Datasheet. You next get this table of part numbers of available TTC filters. Some of them are lit. The ones that are lit have more information in the background. In addition, there is explanation how to perform the part number. By highlighting a certain part number which is lit, for instance in this case 60 picoseconds, you can get the datasheet of this filter. You can start by clicking to download the S-parameter file. This file will enable you to measure the rise time of the impulse response and compare to your specifications, which in return you can feed back to us by saying, I need this rise time to be 3 picoseconds faster or 5 picoseconds slower, etc. On the same click of the button, the outline drawing of the filter is obtained. Your mechanical engineer will be delighted to get this information. After the order is placed, we design the filter per the specifications agreed upon. In this example, we see the frequency response below and the time domain response above, which we send data with every filter we build. We are now going to review Filter Wizard, our filter search engine on KNL Microwave website. It's tapping into 49 years of experience. It's written by engineers for engineers, allowing them to start from inputting electrical parameters, choosing the type of filter, and submitting an electronic RFQ. You can also download S parameters, and you can instantly receive outline drawings and connector types. Starting with entering the filter type, in our example it's a bandpass with an FO 7000 MHz and a bandwidth of 3500 MHz or 50%. Defining the band edges as 3 dB, rejection points on the low side and or the upper side of 25 dB at 4 and 10 GHz respectively. You hit Find Matches and the results page pops up. In this case, we have two possible options. Both of them are thin film. Let's choose the first one, 8AB1-7000E4145, and hit the blue button on the right. The estimated electrical performance of the filter are shown. The filter response shows the S21, S11, and the S21 delay. You can switch and change the bandwidth of the sweep. You can also get phase deviation from linearity. Every point on the graph becomes the spec. So the performance shown to you is actually the spec for us. There is an estimated size in inches or millimeters. And if you hit enter, you get 4 options of installing the filter on your PC board. The entire solution is based on customization. We want the filter to work on your PC board. For that reason, we need the information of your PC board so we can simulate the mismatch from your PC board to our filter. Depending on the method of installment, either by solder or silver epoxy, the appropriate installation will lead. In total, there are 4 types of attachment: the edge wrap, now lit, castellated, open ribbon bond, ground signal ground ribbon bond. For attachment with solder, the edge wrap is lit. In the picture on the bottom right, you can see the filter mounted on your PC board. Next, we require the information of your PC board. Without this information, we will not be able to customize the filter. And the chances that a filter at 10 GHz will be manufactured in USA and sent to your lab and work in your PC board without taking into account the PC board information on your side are slim. In this page, you are required to enter the dielectric constant of your PC board, the trace width, the dielectric thickness, the gap to the ground, etc. In addition, we are also offering the filter in a test fixture that is solely built on your PC board information as shown below. Next, I would like to go over quickly the process that we do at K&L Microwave in order to satisfy a fully customized solution. We start by building a test fixture based on your PC board information. We placed solder paste in different places. We install the filter. We apply pressure. And we're moving the filter through the surface mount temperature profile or through the chambers. At the end, we are proving to ourselves and to you that our filter is mountable on your PC board, as can be seen on the bottom picture. With this process, we also can measure the out-of-band rejection, which can only be seen when the filter is fully solderable on your PC board. Thank you for listening. You have been a great audience. I hope this presentation enlightened the knowledge about reflective and non-reflective filters now available to the marketplace. For further information and questions, please email me at rhershtig@klmicrowave.com. Thank you and see you next time.